Miras. Con idea, vete a YouTube, en principio ya está en directo. Hay un delay de 1 minuto más o menos, ¿eh? You need the PDF, slides, el escritorio.
Por esperando.
Sí, hay un minutito, saldrá con retraso. ¿Cómo se hace? ¿Compartir pantalla?
Compartir pantalla.
Creo que eso clic en eso.
Sí. Todavía no lo veo, ¿eh?
Por eso saldrá, ¿eh?
A ver, estamos comprobando porque todavía no.
Sí, está saliendo.
¿Sí?
Lo que no sé si se escucha. No, tienes que ir en directo.
Bueno, es igual, si tiene que funcionar, da igual.
So I think we can start already at 10:11. So let me today lecture from Alice Della Penna. So I think she did her master in University Torino in Italy, and then she did her PhD and graduated in 2016. Currently was a joint PhD between the University of Tasmania in Australia and the one in Paris, Paris. And then she went to University of Washington to do a postdoc. I guess she knew Evan Mason from here and Barbara Barcelo from here too. And now she's in the University of Auckland as a tenure track position. And she came all the way down from New Zealand here. And of course, she was in Oslo, so she took the opportunity to be here to present something here at the media. And she's interested in all the physical-biological interactions, ecosystem changes. And so today she's going to present predators and prey in the Sea of Mesoscales.
Thanks a lot. Thank you all for being here. I hope everyone can hear me okay. I don't have a very loud voice, so if you can't hear me, just complain. Before I start, I'd like to say that I'm very happy to be here because throughout all my career, I always heard about people working in Palma, in Medea, or at the complex system center. So there were always names that I heard. So I'm really happy to be here. And then I met some great people in the States. So I was really excited to see that Oslo was in Mallorca so that I could come and visit. So thanks a lot for having me here. The work I present today is something I've been focusing on in the last maybe 4 or 5 years. First while I was doing my postdoc, and then now at the University of Auckland. So I think Sam did a great job at describing a little bit my trajectory, and generally my big scale interest is how the oceanic environment, especially at the mesoscale, structured the distribution of marine organisms. I started working on predators, then I ended up working on plankton, and now I'm sort of in between. I think a lot of people here work at these scales, and generally I'm interested in these interactions between ocean currents and ecosystems at a range of scales that are between the upper end of the sub-mesoscale and the proper mesoscale. So I'll be talking today mostly about mesoscale eddies, but generally I look at features that are fronts or meanders or eddies at scales between 1 to 100 kilometers, and from a few days and few months in terms of persistence. If you're not working with these features, they're the oceanic equivalent of weather patterns. They can be found pretty much anywhere in the ocean, but there are a few hotspots where they're really present, and they're really evident from satellite images, from sea surface temperature, but also altimetry and ocean color. And a lot of what we know about how these features affect marine ecosystems is something we have learned thanks to satellites. And a lot of what we have learned is connected to phytoplankton, because we can actually see phytoplankton using satellite and ocean color. But we know a little bit less about how this very dynamic landscape affects larger organisms, and that's what I've been focusing on. In particular, we're learning more and more about the relationship between ocean currents and apex predators. There is a growing number of animal tracking studies that in Europe are often called biologging studies, and in the States they call them more animal tracking. I'm not really sure why, but the idea is that you can put a sensor on an animal, and generally this is done on really large animals such as marine mammals or sharks or seabirds. And then these sensors can track their position in space, but they can also measure a variety of environmental parameters such as temperature and pressure. And this is a field that has been expanding really rapidly. Here I just try to extract the number of publications that had the word animal tracking or biologging. And basically, the numbers keep increasing, and the technology is getting better and better. So we're getting smaller and smaller sensors, which means that they can be deployed on a larger range of animals without interfering with their daily lives. And obviously, these kind of observations give us a lot of insight on how these animals interact with their environment. But there are also lots of studies that look at these observations just as observations from oceanographic platforms. And just to give you an example that I think it really shows the power of these kind of observations, about more than half of the CTD casts that we have right now for the Southern Ocean are coming from southern elephant seals, because they can go to places where ships just can't go, and at times where we wouldn't be able to sample. So for example, in the Southern Ocean, most of the observations from ships are during the summer or during spring or autumn. And generally, we try not to be out when there is bad weather for obvious reasons. Whereas these animals, when they're out foraging, they're just there. So I think these kind of observations are slowly moving us away from the bias that we have in polar regions. So the precision of these tags has been improving a lot, meaning that we went from really basin scale studies all the way to looking at how different apex predators can interact with mesoscale features. And there is a pretty wide range of studies that suggest that different types of apex predators interact with mesoscale features. Most of the studies are about eddies. Now there are some pieces of work that are starting to look at meanders and filaments as well, but they're only a handful, unfortunately. And generally what we have, though, is just a collocation. We get to see that there are some strange loops around the trajectories of these animals. So here I'm just showing an example of a collocation between a southern elephant seals and a mesoscale eddy. So on the background here, we have a map of finite-sized diaphragmatic sonars that are basically giving us the rate of convergence between water parcels. So here we have the very high values. This is calculated backwards in time. So we have the very high values indicating areas such as fronts or the periphery of mesoscale eddies, and the dark areas such as here are the more quiescent parts of the ocean, such as the core of this mesoscale eddy. And the little dots here are the daily positions of southern elephant seals, and they're color coded according to the attempt capture rate. So this specific elephant seal was also equipped with a very small accelerometer that was glued to her jaw. So every time she was doing the movement of trying to catch a prey, like moving the jaw, we can count that event. Something that we noticed first is that, well, these seals are eating all the time, and they're eating relatively small prey, and they're really big animals, so that makes sense. But there is some quite strong variability at the very high values, so that here are marked in white, tending to collocate with high values of FSME, especially at the periphery of mesoscale fronts. So this is just an example, but there are plenty of these, and we don't really know why there is this much. There are some different hypotheses about why that happens, and there are, I think, they can be organized in 3 families of reasons. One is that there is a direct effect of ocean currents on the movement of these animals, and that's something that we actually explored in that paper there. Another one that is really important, especially for large fish, is that because eddies, for example, can have a very strong thermal signature, they may be areas where it's convenient to stay for fish that, for example, needs a specific range of temperatures. But the one that is always called out as the main reason is that, well, if eddies structure the distribution of phytoplankton, they probably structure the distribution of other organisms, and you can have a food web effect all the way to the actual prey of these apex predators. And this is what I will focus on today, because indeed, even if this is the most called out hypothesis for this collocation, it's also one of the least studied ones. And that's how I got interested in this. So obviously the key factor is what kind of prey do these animals eat? And many of them are eating mesopelagic micronekton. That is a really broad label to indicate a really diverse group of animals that include small fishes, crustacea, and squids that are typically a few centimeters in size. In particular, many of these apex predators feed in the mesopelagic, so between 200 and 1,000 meters deep. And they're not plankton, they can actually swim. And they're really important for marine ecosystems just because they connect the planktonic food web with larger organisms. Something else that is catching a lot of attention about these organisms is the fact that they play probably a very important role in the carbon cycle. And I say probably because the error bars around their contribution to the biological pump are quite large. And that's why there's a lot of effort in understanding better the mesopelagic at the moment. But because many of them migrate from the mesopelagic to the ocean surface every day, they're likely transporting lots of carbon up and down the water column, well, mostly down. So these are really important organisms in the pelagic food webs, but we don't know much about them. Partially because they're really hard to measure. They're too small to put an actual tag on them. They spend most of their time away from the surface, so we definitely can't see them with the current satellites we have. And their distribution varies at really very many different scales. So the key approach we use to study their distribution is to use the sonar acoustics, and that's what I will be showing a bit more today. But the other key method is to just fish them. And this is midwater trawling. More recently, the technology has been improving, so there is some really exciting underwater video that I think is going to bring some big change in that space. So they're hard to sample, but nevertheless, because these organisms are important, there is quite a lot of work and effort in trying to understand how they're distributed in the ocean. And especially because data sets have been accumulated throughout the years, we start to have some biogeographical maps. So here I'm just showing an example. There's a bunch of them from people who have collected all the acoustics data they could get, and look and basically sketch some distribution of the biomass or diversity of these organisms. Then they're being related then to large-scale environmental patterns. And some people even made projections about how this might change in the future. So I think this is great. It's great that we start to have this. But from my perspective, these are the large-scale biogeographies, but that's not the landscape that apex predators encounter, where they go out on a foraging trip. Their foraging trips are about a month or two. They don't see this variability. They see the mesoscale. They see the sub-mesoscale. So what is the variability of these organisms at these scales that are the ones that predators encounter? So I'll be presenting results from two different studies. The first one was in the Northwest Atlantic, and it's part of the NAMES project that was funded by NASA between 2015 and 2018. The area of study is actually, I should have put a map, it's here in the logo, it's the yellow triangle. So it's between the east coast of the United States and Greenland, I would say. NAMES was about phytoplankton and their impact on the atmosphere, but the sampling strategy was really convenient for this kind of study because there were 4 surveys in the same area during different seasons. And there was some interest in sampling eddies. So throughout the entire project, we managed to sample 7 cyclonic eddies, 6 anticyclones, and 11, we call them out of eddy stations, that are stations in areas where the closest eddy was maybe a couple of 100 kilometers away. So we think definitely a little bit out of the direct influence of these features. When I talk about sampling, I'm mostly talking about sonar acoustics. So the key principle behind this approach that is the same that is used in fish finders is that you're sending sound down the water column, and when sound encounters something that has a different density, it's reflected back. So by measuring the intensity of the reflective signal and the time delay between when you sent the signal and when you got it back, you get a sense of how things are distributed in the water column. And I'm deliberately saying things because one of the key limitations of this approach is that you don't really know what kind of organism is sending you the reflected signal. You can get some information depending on the different sound frequencies you use, but you are never going to be able to, at least for now, you're not able to say it's this species of fish at this life stage. And that's a little bit frustrating. But nevertheless, it's not a particularly invasive approach. And at most times, it's an instrument that is present on research vessels. So you turn it on. You make sure it doesn't interfere too much with the ADCP. Or you can also use the ADCP for this kind of measurements, and then you see what you get. So the first thing we learned from these acoustic studies is that the gradients we observed near the surface were reflected in the mesopelagic. And I'd like to show this with a specific example of anticyclonic eddy we sampled in 2016. This was in spring. And here we can see it's sort of sea level anomaly portrait with the ship track that is marked here in gray. And the portion of the ship track I'm presenting the observations for is this one here in white. So we went in this way and then out that way. Here we have a space series of the density near the surface. And basically we use that and a bunch of other tracers to classify our observations depending on whether they were inside the eddy core or at the periphery, and then when we transition outside of the eddy. I'd like to say that this wasn't really the plan. I think the idea was to stay within the core of the eddy. The plan was to try and be Lagrangian, but there was a variety of changes in weather that changed the strategy of the sampling. So these are the near surface gradients. And if we look at how they're reflected in the acoustics, we have these sort of echograms. So here we have to do a bit of mental gymnastics because this is a space theory, where this is an echogram where we have depth on the y-axis and time on the x-axis. So this is referring to this first chunk of observations that were inside the eddy core. And we can see some typical structures that we see in these echograms. The different colors indicate the intensity of the reflected signal. And here, for example, you have the Della vertical migration, where at night you have a lot of organisms near the surface, and during the day, not so much. And we have this very thick and very reflective deep scattering layer. You can even see here how different types of weather changed our observations. Here it was when the weather was pretty calm, and here was just after a storm. You can see there's a lot of noise. But what's constant is that there is this very thick, deep scattering layer in the core of the anticyclonic eddy. As soon as we move out of the core of the eddy, things change quite dramatically. First of all, near the surface, there was a lot more backscattering, whereas this deep scattering layer sort of got skinnier and less reflective. And this was a really sharp gradient that matched the gradients near the surface. When we moved completely out of the eddy, there was another change. It's harder to see because the echo sounder was off right at that time. But even if you just compare one side with the other, you would see that there are some differences. And this is something we were a little bit expecting, but probably not in such a sharp way. Well, I wouldn't have expected them to change exactly at the same location. But the other interesting result was this very big difference between the acoustic backscattering in the core of the anticyclones and outside. And this is not something we saw inside that anticyclone, but it was a pattern that we found pretty much in all anticyclones we found. So here we're looking at the composite of the seasonal anomaly of acoustic backscattering. So these are profiles with depth. And basically, if there was no trend with the polarity of the eddy, we would expect everything to be stuck around zero, with the profile of the acoustic distribution being around the average for each season. And we have profiles for the stations outside of eddies, and that's the black line, inside cyclonic eddies, and that's the blue one. And in the red one, inside anticyclones. And we can see here that in the mesopelagic, we have this big positive anomaly inside anticyclonic eddies. This is the average nighttime profile, but we have to keep in mind that a lot of these animals migrate, so we also have to check what's happening during the day. And we have a similar pattern, which suggests that this anomaly in acoustic backscatter inside the core of anticyclones is not caused by animals that migrate. They are the residents of the mesopelagic. This is not a result we expected, and we're actually still trying to make sense of it, because this result suggests that anticyclones in the North Atlantic are characterized by a very strong acoustic backscatter. And this might mean different things. So this acoustic backscattering is generally used as a proxy for fish biomass. And if we believe in that approach, it means that we would have more biomass in the mesopelagic inside anticyclonic eddies. And this was a little bit of a puzzle, because if we think about the impact that these eddies have near the surface, for example, on near surface chlorophyll, it's pretty much the opposite of what we expected. So here we're looking at composites of near surface chlorophyll, and these are composites depending on eddy polarity. And this is for anticyclones. So we have less chlorophyll inside the core of anticyclonic eddies and more chlorophyll inside the core of cyclonic eddies. And this is why we're a little bit puzzled, because it would mean that inside anticyclones, we don't see that much chlorophyll near the surface, but we see a lot of acoustic backscatter at depths. So why is that happening? There are a few hypotheses we have. One is that this is an image that is biased by the fact that we're looking only at the near surface signal. One of the properties of anticyclonic eddies, is, especially in that region, is that they have deeper mixed layers. So there may be more chlorophyll, it's just that it's diluted over a deeper water column. So there might be actually more food there, it's just that we don't see it. And the other thing we're thinking about is that maybe, especially because anticyclones are warmer, there may be a different ecosystem that is just more efficient at transferring biomass all the way to the mesopelagic. But this is always if we believe that this more intense backscatter means more fish. And that's not always true, because actually what we're looking at is that we're just looking at the reflected sound. So what may happen is that inside these anticyclonic eddies, there aren't more fishes, there aren't more organisms, but what's there is a different community that for some reasons reflects sound better. For example, the fish bladder may not have air, but may have oil, and then the sound is reflected differently. This is definitely a possibility. But then why does this happen is something that requires another explanation. It is somehow a combination of the two above, and are these eddies actually trapping a bunch of organisms from a different ecosystem where the eddy had originated and just carrying them around as they travel in the North Atlantic? And that's something that we've been exploring in the next study. I was really excited about this hypothesis because there's quite a lot of work about eddy trapping for biogeochemical tracers, but these are fish, they swim. So I was curious to see if it's possible that this happens as well. So to explore this question, we actually went back to a data set that was collected even before the last named missions. And we're completely changing region. We're going to the Southern Ocean and looking at a data set referring to what is called the eddy voyage that took place in, well, it's the southern autumn of 2016. We left Hobart, Tasmania, and headed south to sample this cyclonic eddy that had detached from the Sub-Antarctic Front about a month before our sampling. And I should say that, again, this was a mission that had nothing to do with fish. It was mostly about biochemistry and eddy physics. But the sampling of this eddy was actually really convenient because we basically spent 1 month sampling the core of the eddy, identified here in red thanks to the ADCP data, the eddy periphery in yellow, as well as the ambient waters of the subantarctic zone that are here in blue, and most critically, the waters on the other side of the subantarctic front here in black. And that's where the eddy had come from 1 month before our sampling. And luckily, from the perspective of this study, for the entire time, the echo sounder that was on board was pinging. So we had observations of acoustics for all these shipwrecks. So generally, the distribution of acoustic backscatter in the area follows a bit of a pattern that hasn't been documented that much, but we're starting to see this in different regions of the Southern Ocean, where you have a lot more, this is the integrated acoustic backscatter over the portion of the water column we can observe. Generally, north of the Sub-Antarctic Front, you have between 2 and 5 times more reflected sound compared to south of the front. So there is this very strong gradient in acoustic backscatter. And that's also what we found in our sampling. So these are the integrated values from the subantarctic zone. And in the polar front zone, we have basically about half of those values. And interestingly, in the eddy core, we have something that looks very much like the waters from the polar front rather than the surrounding waters. And this is after a month that the eddy had been away from that area, wandering around, that I believe exchanging waters with the surroundings at the eddy periphery. And it's also something that we could observe in the average profiles of acoustic backscatter. So we have this is the average daytime acoustic backscatter profile for the eddy in red, and for the ambient waters, so all the water surrounding the eddy in blue here. And here you can see the very strong difference in the mesopelagic, which is actually responsible for this big difference here. But interestingly, if you look at the average profile in the polar front zone that is in black, that looks quite a lot more similar to the eddy core compared to the subantarctic zone, the eddy core profile looks a lot more like the polar front zone compared to the subantarctic zone, meaning that it looks more like the origin water than the waters that it has around. yes, this is just to illustrate these differences. Interestingly, these similarities and differences are modulated by depth. The portion of the water column where we have the strongest pattern is between 200 and 600 meters. Near the surface, the eddy core basically has some properties that are really in between the ambient waters and the origin ones. And deeper than that, it actually looks a lot more like the ambient waters than the origin waters. So it means that the currents of the eddy are not playing the same role at all depths. And just to reinforce that message, if you actually look at the differences between different parts of the eddy and the ambient waters, the eddy periphery is basically something in between the eddy core and what's around it. And things are exactly the other way around if you do the comparison with the polar front zone. This suggests that while the eddy core is more similar to where the eddy had originated, the eddy periphery is starting to look like the ambient waters around. So what does this mean? Does it mean that the fish is trapped or not? Because that was the question I was trying to answer. Spoiler alert, I still don't know, but I think this is kind of a useful step in that direction. Well, eddies can be highly nonlinear. The eddy we sampled was quite a champion in nonlinearity. Here we're looking at a profile of the nonlinearity parameter. So the ratio between the rotational velocity and the translational velocity of the eddy. And generally, a threshold that people have been using is 1, and it's this black line. And for basically all the first 1,200 meters, we were way above that, but with a decreasing effect, suggesting that the eddy became less and less trappy as we go deeper in the water column. So if we consider, yes, go ahead.
So what's the relation between trapping and nonlinearity of the eddies?
So here we're using nonlinearity as an indicator for trapping.
So the more is
so the more the rotational velocity dominates over the translational one,
okay,
the more the trappier, the more trappy it is. But it's just a proxy. We did calculate, for example, eddy retention from satellite altimetry. It was really retentive, but unfortunately, we can't really go below the surface with that. So this is calculated from the ECP. So that's why we have a nice profile.
And how do you estimate the translational velocity?
So my collaborator, Ram Patel, did that. I think we used
It was visible from altimetry. From track it from
yes.
eddy tracking. Or
so I think we calculated that from altimetry, but then I think for this profile he only used the ABCP and he decomposed the two, the rotational and the translational. But I don't know if for the translational velocity, because I remember he tried different methods, and one was to project some filtered version of the ABCP velocities on the current trajectory from altimetry. But I'm not sure if that's the approach he used in the end. But I can check because we have it.
And the vertical, sorry,
yes,
so this is vertical speed. So this is vertical velocity.
No, this is the velocity of the fish. I'm getting to that in a second. So this is about the eddy. So if fish was completely passive, it would have been totally trapped by this eddy. However, they're fish. Some of micronekton is squids, so they actually swim quite fast. But exactly how fast is not something we know very well. So there are some studies. The problem is that they're all in other regions and for commercially important species, so we don't have a huge range of species as well. They looked at how fast these fish can swim. And so these are the speeds.
Fish.
From fish, yeah, not from the currents. And generally they swim about basically 1 body length per second or half a body length per second. The other key factor that I think is that there are different ways of swimming. When you're a fish, they can be really fast when they're escaping a predator, so it's like a sprint for us. But I don't think there would be good marathon runners. I don't think if they can sustain long sections of intense swimming. But the truth is that we don't really know because they're really hard to observe. But then what's interesting is that because we know the size of the eddy and we know how fast they can go, we can calculate if they had a time in 1 month to swim out from the eddy center all the way out. And we did the math, even if it's really a back of the envelope calculation. And actually, if you take the center of the eddy and you use this velocity and calculate if they could have got out in a month, the answer is yes. But only if they always go in the same direction and they always swim at full speed. And I'm not sure that's realistic. But I think maybe that's not the right question to ask, because the question is there a point in going away from the eddy for them? Because if the eddy is trapping water properties, it's potentially trapping their prey. The temperature inside the core of the eddy looks like the waters where they had originated. The habitat of the fish didn't change that much in a month. So why would they want to swim out and go back where they came from? I think this is true for the eddy core, but the eddy periphery is an entirely different story, because even in the modeling papers from the early 2000s, for example, we can see that eddy cores can be really trappy and the peripheries can exchange quite a lot with the ambient waters. And there, I think there can be some interesting interactions where maybe planktonic communities mix, or maybe the temperature changes, and that could motivate a fish to go one way or another, but that's over smaller distances. And something else that I think is really important is the fact that to move, these animals need to feel a gradient. Otherwise, how do they know in which direction to move? And the gradients on the horizontal for mesoscale eddies are still over a pretty large distance compared to the size of the fish. So unless they are able to feel the speed through some pressure things, I don't know if they can actually feel the difference in temperature that is associated, for example, with the periphery of a mesoscale eddy. But there's a lot that we don't know, so there's a lot more work to do. And I think a main limitation of this study is that here we have 3 profiles, and we're pretending that these 2 are at the same time, right? We're looking at whether the eddy core is more similar to the polar front or to the subantarctic zone. But actually 1 month has gone in between. I think the way to figure this out is to go Lagrangian and stick with the same eddy and have different measurements at different time steps. How to do that in practice, that's another question, but I think that would be a good direction to go. So to sum up, because I think I'm slowly running out of time, and in terms of apex predators and their prey, mesoscale eddies basically present a unique habitat compared to whatever is around. And in the North Atlantic, for example, we found this very strong acoustic backscatter in the core of anticyclones. I think this is a really interesting result because it forces us to think about how we look at eddies. And anticyclones in the North Atlantic have been called by some people for a long time ocean deserts because there was not a lot of near surface chlorophyll in the surface signal, but maybe that's just not what's going on there. Trapping of origin waters might be a key mechanism in this, and this is what the results from the Southern Ocean study suggest. But yes, there's a lot more to do. But before I conclude, I'd just like to step back and get back to the question that got us there. What does this mean for apex predators and all these collocation studies I mentioned in the beginning? And basically, these eddies are a different ecosystem for that these predators can access without having to travel maybe that far as if they were following a basing scale gradient. And this means that the prey may be more abundant or more accessible just because maybe it's shallower and they tend to dive a bit less. So this means that if there is any change due to interannual variability or long-term variability in the distribution of where eddies are, the foraging areas of these predators might change. And how frequently these eddies are and how trappy they are, if all these properties change, the environment for these predators is being altered. And I think there's some potential of predicting this thanks to the ocean modeling that we do and what we know about mesoscale eddies, and potentially even inform some conservation and management policies, because these features are really part of the environment the predators navigate. And with this, thanks a lot for your attention, and I'll be around all of today if you want to chat or if you have any questions. And thanks again for being here.
Thank you very much, Alice. Very nice. We have plenty of time for questions. Anyone have a question for Alice? Either biology or physical? Sure.
Yeah, so it was really interesting. And as you were saying, like in the middle of the eddy, maybe they don't feel the need to move. So what happens if you kind of focus on the edges, on the frontal regions, and also you have like other geochemical fields you said. So do you see like any relationship, any difference like between outside and in the inside part? Because then you see like they prefer to stay outdoor.
Yes, so the tricky thing with the periphery is that things are really variable. So while in the center, you get pretty uniform waters, in the periphery, even depending on which direction so if you look at the, So we basically have 1, 2, 3, 4, 5, 6, 7, 8, 9 transects across the periphery. And we looked a little bit into that, but I know it sounds crazy, but 9 transects don't seem to be that many for that analysis. And part of the reason is that half of this is during the day and half is during the night. So you have to sort of check away half of your data, because during the night it's very hard to see the gradients because a lot of organisms are just near the surface. The eddy had a really strong differences in the biogeochemical fields. So one of the ways we were tracking the eddy was from altimetry, but the other one was just because in terms of near surface chlorophyll, it was a lot less compared to the surrounding waters. I think something really interesting is happening at the eddy peripheries with zooplankton, because we had a triapsis in the water, and we did, I think, 2 transects across the eddy center all the way to the periphery. So the triapsis, I don't know if you know, it is a little bit like an MVP, and it had an optical plankton counter. And we found this really weird structure. Unfortunately, it could only go down to 200 meters. But you had that on the periphery of the eddy, there was lots of zooplankton. And then there was this sort of, imagine the shape of a volcano with very high values of zooplankton on the 2 peripheries, almost nothing in the center, and then very little outside. So I think the eddy periphery could be a very good foraging ground for micronekton. So something that might happen is that they try to stay on the periphery. But the problem is that the different sides didn't look exactly the same. And I don't know if it's a matter of mixing or it's just that we didn't have enough profiles to figure that out. But that's, I think it's one of the things that we need to think more about, because in a way, the eddy core is the simple part because it's more coherent.
And what are your plans in the future?
I'm trying to
more field data.
Yes, so I'm still trying to figure out this.
With more data, or just with the data you have?
At the moment, just with the data I have, there is this big. This is from the Australian Observing System database, and New Zealand is also participating to that. So there's a growing body of observations from acoustics. So something that I'm planning to do, and I actually started, but I've just been a bit slow, is to extract the position of eddies and compare them to these shipwrecks across different seasons and see if in the historical data set we find a trend as well, because the one eddy is not enough to say much. One of the things that are really interesting me at the moment is that there's also this inconsistency for example, in this map, you see you have this very strong backscatter north of the front and almost nothing south. And there are some studies where they did acoustics and midwater trawling. And in the midwater trawling, they don't see such a big gradient. So we don't know if it's a limitation of acoustics or if it's because there is more squid north of the front and we're just not good at catching squid because they are so fast at swimming. So actually one of the things I'm working on is to try and use underwater optics to see if we can detect organisms in the mesopelagic as well. But those are the two directions I'm moving towards. But I think something else that I'd really like to do is just some modeling work about this strapping idea, where you have basically a Lagrangian simulation, but instead of having a tracer, you have a tracer with some movement, and just to see, even with an eddy that has the same properties as the one we sampled, how many of the trajectories get out if we make them move in ideally a biologically plausible way. So that I think these are the three directions, because I think the study, the Southern Ocean study especially I presented, has this limitations of being just one eddy. Acoustics is not perfect. And we just don't know that well how these organisms move. And I haven't found a way to address all these issues together, but if we do a little bit in those three directions, maybe we can move a little bit forward. But I think ideally, the ideal study would be to be Lagrangian and just sit with an eddy and watch it change. But that's a bit challenging on an operational level, especially in those areas.
So you want to focus really on eddies, continue on eddies, because as Danny was suggesting, I think it would be nice also to look at fronts.
Yes.
That reason Danny has developed, well, there are all techniques that you can detect fronts with satellite images, so that in the Southern Ocean or in close Antarctica, maybe we'll get lots of clouds again. So, but maybe you can apply it sometimes to identify fronts from mesoscale ocean colors. So with altimetry, the way that they are built, all the gridded fields is like you don't get really the fronts. It's difficult to, well, at large scale you can get something that you get better the eddies than the fronts, but with other satellite images would be nice. Because I remember once, well, maybe baptism was more, but with the bluefin tuna here in the Balearic Sea, I think it's usually concentrated more in frontal areas more than
yeah, the hypothesis probably equal to salinity in that case.
Okay. Yeah, I had started some work on fronts while I still was in Seattle, and then it got I got a bit sidetracked by the new job, but because for the names field data, we actually have, I think we may have some, because at some point I had some backup slides. Yes. Yes. So I won't go too much into the details, but so for the 4 names metrics, the station data were, I don't think they're ideal for this analysis, but for all the transit data between Woods Hole and basically that area in the center of the North Atlantic, we had the ADCP on all the time, not the echo sounder, and that's a little bit upsetting. But ADCP data can be really good if you are not trying to quantify biomass and you just want to look at the gradients. So I've been looking a little bit at the relative acoustic backscatter across these fronts. And so far I have some results. I'm a bit puzzled because I have that basically in the near surface backscatter, you get very similar patterns as what you get if you look at the fluorescence. So if I match the gradients, so for example, I was using gradients in the thermosalinograph to identify fronts, even if it depends on the direction of the fronts. But I was just comparing the gradients in the thermosalinograph with the gradients in the acoustics, in the epipelagic and the mesopelagic. And I found that in the epipelagic, so near the surface, things follow very much what chlorophyll is doing. But once you get to the mesopelagic, that match between the gradients near the surface and the gradients in the mesopelagic holds on only for fronts that are like the peripheries of eddies, but the smaller features,
More surface.
it looks like in the mesopelagic doesn't have a lot of effect, and it makes sense because a lot of them are mixed layer features. But the time I'm sort of a little bit stuck with this study because if I use the finite size Lyapunov exponent, let's say, to find the gradients, there's always some small shifts because they are derived from altimetry. And for example, if you look at this ridge of FSLEs, it's hard to see if it's matching with that gradient in the acoustics or with that, or if it's not matching at all. So it becomes a little bit tricky to figure out, to map the two. So I'm more tempted to use the thermosalinograph. But then there is all the issue of the direction of the front. So I'm still thinking about that. And in some other regions, I think altimetry does a little bit of a better job. I'm thinking about Alberto Aldena's paper in he did an analysis like that with the FSLEs, and he had a very good match. But I think he was also looking at the fronts and the impact on the epipelagic morphish. Whereas I really like to go and see what's happening in the mesopelagic. But that's definitely something that I think is interesting as well.
Well, actually, I have a question.
Yeah.
It's regarding the eddies that detach from the ACC fronts.
Yeah.
So I can see that it's very like positive impact on the advection of nutrient or sea leakage from the southern from the ACC to the lower latitude. But now I'm thinking, like, if you think that all these fish are trapped inside the eddies and then they move north, then it says like this has a negative impact because when the eddy will decay, then those fish will not adapt, or they're willing to go back to where they feel.
So that specific eddy, so we sampled it after 1 month after it was born, and then it was actually reabsorbed by the meander 1 month later. So we got it at the midlife.
Okay.
But the thing is that in those 2 months, the eddy, especially the periphery, is exchanging. So in a way, I think it's slowly leaking fish through the ambient waters. And I don't know if they can adapt, because the thermal difference of a few degrees, especially in the mesopelagic, it had a very strong dominant isopiclas. So one of the problems is that for these organisms, we know so little about their physiology. I'm not a fish expert, so every time I found something about this, I was asking to people who study mesopelagic fish, and a lot of things we don't know, even how long they live. And we say, oh, a few years. So even if they're small, they live quite a long time. So I suspect they must have some degree of adaptability, but I don't know. But it's a good question. What happens to those organisms?
In this case, it's also impossible. So at least they can trap water from the south.
I would say so. Yes. Yeah.
Then maybe you should see in your deposit more biomass.
Yes. Yeah. That's what I would expect. I think with the historical data set, that's something that we could check. Yeah. Yeah, but what I find that is a bit frustrating with the acoustic data is that you think you have a lot, And then you start taking away sunrise and sunset because they're moving, so it becomes complicated. And it's like, okay, they're less. Then night is a bit tricky to find gradients because so many organisms are just near the surface. So in the end, you have a lot less. But I think what's really interesting is that a lot of ships have ADCP. And there are a few really nice data sets, including I think it's managed by the University of Hawaii, the JASADCP. And there are lots of tracks there. So I'm collaborating with a student who's always trying to put all these data sets together and see if there are some relative measurements that can be standardized. Because I think there's enough data. It's just that they're all spread around different institutions and different labs. But for example, I like the Australian portal quite a lot because they are all processed following the same method. But it's hard to do that at a global scale. I think that's
future.
Yes.
Yes.
Any other questions? Well, thank you very much, Alice.
And I'll be around today if you want to talk about anything. Thanks. Okay.
Oh,
I